So hello, welcome everyone to the first ever webinar of Dingrastro Club, collaborated with AACK Nebula. So before starting our webinar, I would like to introduce you to Aluna, who is the founder of AACK Nebula Kosovo. And I would like to invite Aluna to speak and tell you about her club before introducing you to Dingrastro Club and starting the webinar. Aluna, please.
Yes, thank you very much for having me. I am Aulona Chaka. I am from Kosovo. I am the leader of the Nebula group, which is a group that is basically dealing with astronomy outreach. We do astronomy events with a telescope where we show the public the universe, like the moon or planets. This year, I also got the chance through the Tech Girls program to visit the NASA headquarters in Washington D.C., which was one of my top arrivals. So Nebula is founded on was founded on 2019 and is going strong with 50 members. And we're so excited to collaborate with you in this event and hopefully in future events. Thank you.
That's super cool. Thank you, Luna, for your information and introduction to your club. So, wait a second. Okay, introducing you to Dingrastro Club. My name is Jashanpreet Singh and I'm the founder of Dingrastro Club. This club was founded on February 13, 2023, in the view to expand the knowledge of astrophysics and astronomy worldwide. So if anyone want to be the member of this club, you can direct to this website. And if you want the updates of our upcoming events and seminars, as well as star parties that will be coming in my city, as well as the nearby cities, you can be updated on Instagram as well as all the groups that are there in WhatsApp, Instagram, and Discord. And we are also on YouTube. All the codings for these webinars and the upcoming webinars, Python courses for astronomy data analysis will be updated on our YouTube channel. And all the code of the Python analysis will be uploaded on our GitHub ID. So before going ahead, I would like to show you how you can become a member of our astronomy club. So wait a second. Yeah, this is our website, dingrastroclub.github.io. If you want to be becoming our member, you can directly click on this button. And this is the other info of our club. And there are weekly facts of astronomy and astrophysics that will be uploaded and updated weekly. And after clicking on this button that is here, you will be directed to a Google form. After filling this Google form, you will be added soon to our club. Moreover, there is my own website in which I post my researches, astrophotographies, and you can check them on this website that has been uploaded as jstingra.github.io. And if you want to check my research, you can directly go to academics part and then direct to the research part of our website. And you will be directed to this page. It's not a full research, actually. It's only a summary or a paragraph that it includes this, what the graph and analytics of the supernovas, pulsars, sun, as well as the nebulas you can see here. So not further ado, we will be moving on the main part of the webinar. So let's get started. So basically, we will be more doing of supernova rather doing dark matter, because dark matter is the most stuff, and supernova is the one of the main part of my researches that I did in past weeks. So I will very glad to tell you about the supernova and about my researches and other things about some of the BSc stuff that BSc student and undergrad student do. So the outreach of today's program is dark matter and Taiwanese supernovas. And moving ahead to dark matter. So dark matter is mainly considered as the missing mass of astronomy and astrophysics by the evidence that was given by two physicists. So moving on, the evidence of the dark matter, sorry. So the first evidence was given by Zwicky in 1930s. He studied the coma cluster. Every coma cluster is considered in abels. These are the, if you see, these are the galaxies in considered as abels. Every abels is a coma cluster. He did the research and concluded that the middle galaxies, these type of galaxies, were moving with the escape velocities. So mainly the escape velocity is the velocity by which, if someone moves with the escape velocity, it fly apart in the space, leaving the source object which he is orbiting. It is orbiting. So the formula for the escape velocity is under root of, pardon my handwriting, is 2 gm by r, where m is the mass of the source object, and the radius is the how big is that cluster or source object, and g is the universal gravitational constant. And if anything moves with this velocity or more than this velocity, it will be escaping apart from the main source object. So for example, if we are studying about the satellites or the rockets, we used to send rockets on Moon, Mars, etc. Like this only. After giving the orbital velocity, just orbital velocity, we have not included the 2 in the orbital velocity. Our velocity formula is gm by r square, root gm by r square, whereas the escape velocity formula is the root 2 times that of orbital velocity. So just like that, satellites move in the orbit with the orbital velocity, and it is constant for every sources. And if we're talking about the rockets, how they escape is with a constant or more than that value of the escape velocity for a given source object. So it is inversely proportional to the r, that is the radius of the source, and directly proportional to the under root of m, that is the mass of the source. So talking about the dark matter, so he concluded that the coma cluster galaxies and the stars were moving with escape velocity. That means they have moved apart 1,000 or million years away back, but they were still at that place. Even if we study the Abel, they are moving with the escape velocity and they are at their position. That's really cool. But how it happens? So in his paper in 1930s, he concluded that there is something missing mass that is binding the galaxies along with the gravity itself. So that missing mass was named as dark matter, which is pushing. Oh, wait a second. 10 minutes. Wait a second, please. I don't know what is happening. Okay, no problem. I think this meeting will be ended. I don't know why. Please rejoin the meeting. I don't know why it is giving this message. Let me see. Okay, so please rejoin the meeting if it ended in 10 minutes, as the time should be 40 minutes, but I don't know why it is ending in 20 minutes. Okay, so moving back to the dark matter. So the main part of these wikis astrophysics knowledge paper was there is something missing mass that is binding the galaxy clusters and not letting them move away even if they are moving with the escape velocities. So that missing mass was named as dark matter simply. Moreover, if you want to study about astrophysics, I would be sending and group the PDF of the book of Neil D. Tyson, Grace Tyson. The Astrophysics for the People in Hurry that I have read. It's very amazing, and it covers all the topics of the astrophysics very neatly and very briefly. So that's an amazing book. And one thing you should know that dark matter and dark energies are two different things. Don't let them mix up. As their names are similar, but they are two different things. Dark matter consider the property of gravities, a little property of gravity, and dark energy includes the property of particles. So moving ahead, this would be a sample image how our universe would look like if there is no dark matter. All things will have fly apart if there will be no dark matter in the space. That's really super cool if our Earth will be flying apart from the sun, but I don't know. However, it will be deadly for us, but it will be cool. So this will how it will look like. This is the present image of our universe, including the dark matter, and there is 75% or 75 to 78% of dark matter in the space. That's awesome. And without dark matter, everything in the space will fly apart. So the second evidence was given by the astrophysicist Rubin. In her time, she studied the spark galaxy, the active galaxy nuclei. Most of the research paper of the Rubins are considering the spark galaxy, which is just an awesome thing. She used to study the redshift and phenomena of the objects in the spark galaxies. So what she studied that the objects which were near to the center of the spiral galaxies were moving much smaller than the objects which were far away from the galaxy center. This was a graph or a plot that she built. See how the light years of the distance in the light year is very less, and the velocity is also less. As we move apart, the velocity increases as the distance increases. So velocity is directly proportional to the distance. But the exception was accepted was that it will be decreasing with increase in the distance. The velocity is inversely proportional to distance, but this doesn't happen because of the visible disk. More is the mass, more is the velocity. But at these apogees of the galaxy, the speed was much less. But the speed was much greater. So she included that this space was something filled by the missing matter that is increasing the velocity, orbital rotational velocity of the objects in the galaxy. So that space which was filled by the dark matter was named by her as a dark matter halos. So this was mainly the evidence of the dark matter and a little bit about the dark matter. So dark matter is nothing but a missing mass and the missing mass in space. So we are currently researching on it, how we can find it, because it's not visible to us, not visible to human beings, but I think that it can be visible to other organisms because there are other organisms have many features. For example, the dolphin has different sound waves, etc. If I'm right, and just like that. So I think that there is other organism that can see behind what human can see. So that's my thought. So moving on to the yes, this is a simulation not built by me, but a simulation from an undergrad student. There was so if you see here, the objects are moving with less rotational velocity, whereas this that was observed. This objects are moving with much orbital velocity or rotational velocity. That's the thing to be studied in the case of dark matter. So yes, the favorite part of this webinar was the type 1a supernova. So the type 1a supernova is the supernova that occur in the binary system. The binary system of two stars one must be the white dwarf, and other can anything from the giant red supergiant to the brown dwarfs. So what makes Taiwanese supernova different is their light curves. They have a super amazing light curve. If I draw it here, a sample light curve that's from the original data. However, I will not able to make it like that, but I will try. Wait a second. So the sample plot was like this. Here was the brightness to the time curve. So this was like this, like a mountain, which here it indicates the nickel decay, and here which was accompanied by the cobalt decay. This indicates that it was very high energy decay of the elements when these supernova occurs. So this main light curve make it awesome and difficult to study actually. So if anyone want to study the features of the binary system, you can direct to this website. For example, let me show you how this works. I don't know if it is showing in your screens. Wait a second. Yes, so this is how it look like, the binary simulation. This is made by the Michael Toppings, written by Michael Toppings and made by the Python analytics. And this here you can adjust the eccentricity. Oh no, it won't. And here is the radial velocity to the time curve of each of these subjects. And here even you can adjust the masses. This I have sent in my astronomy groups also, astronomy club group, and you can check there also. So back to our webinar PPT. Okay. So this was all about the Taiwanese supernova, just introduction, and moving ahead. So yes, this was the light curve of a sample, the real supernova, that's S2018 GV. This is the how brightness time curve, and it is easy to understand because as the brightness increases with time and decreases with the time, as the time increases, it decreases. And when the time was starting of the supernova, the brightness is high. So it's easy, nothing to explain. Yes, this is the life cycle of the supernova. As I was previously talking about the red supergiant, let me tell you how this cycles works. So the main star is built from the gas giant clouds. So when the gas giant cloud in the space collapse under their gravity, so they become the protostar disk actually. After this becoming a protostar disk, they combine into their own galaxy. The core forms in Titori phase, and then depending upon the mass and the fuel of the stardust, the amount of stardust, two types of stars will get. So what is basically time dilation? I told you that this is how time equation looks like. And if the speed is less than the speed of light, just how in the case of what is rotational velocity is much lesser than the rotational velocity, the speed of light. So this part will be going to be positive. The underroot part going to be positive because this factor will be in the under fraction or the decimals. So this will be giving our positive time. That means time is going ahead. That is we are going in future. So moreover, if the speed of the Earth or object moving in the space is equal to the speed of light, the time will be going to freeze because this factor will be becoming zero, and this time will become infinite because something in the denominator, zero in the denominator gives infinity. That's not defined. So this will be giving infinite time. That means this photon will have to take infinite travel for one tick. That means the time will going to be freezing. That's really awesome. If you think the time will freeze, it's really awesome. So if you think of the speed of light greater than the speed of, the speed of the source greater than the speed of light, actually that can't be possible. If you think when it will be reaching the speed of light, the time will freeze. Actually, it will be not going to move ahead, not going to move back. The time will going to freeze. Nothing will happen when we move with the speed greater than the speed of light. And one thing here, if you see, if the v is greater than the c, it will going to give the value greater than the 1. That means there will be negative in the under root, that will giving the value of time in iotas. That is a complex number, and this will ultimately give a imaginary value of time that's can't be possible in real time. However, I don't know if in future someone define infinity in the real numbers, or in and imaginary numbers give in something like can define the imaginary numbers in the real space. That can be possible. I don't know. In my view, that can be possible. However, so this is also a good thing you can see here is how to calculate the recession velocity and redshift. It's much simple. And what we need is the observed data set or spectrum of a object you are studying or you are researching, and the theoretical data set or a theoretical spectrum of the object you are studying. So, for example, if you see here, wait, let me on the pen. So, if you see here, here is the spectrum and absorption lines. These lines that are going down are known as the absorption line in the astronomy. So these absorption lines have certain wavelengths. For example, this is a theoretical spectrum of a sun-like star. And if you see here, these are the absorption line of specific elements, have specific wavelengths. If you see here, and if you compare the it with the real data, you will see that there are some matching in this two spectrums. So how we calculate the redshift actually is we zoom out the original data and calculate the lambda of the specific element that we want to study in that galaxy or anything extragalactic. And we calculate the difference in the wavelengths. The difference is lambda naught minus lambda theoretical. Lambda naught is the velocity, is the wavelength of the observed, that is in real case, and lambda theoretical is the what we study in the theoretical part or the laboratory that we got in the prediction from the simulations or the spectrum that we built using computers. So if you see here, the formula for the redshift is actually z is equal to delta lambda by lambda laboratory. Lambda laboratory is again that the theoretical wavelength calculated by computer. So what we do is we calculate the difference in the lambda, just how we get in this case, and divide it by the lambda laboratory or lambda theoretical. This give out the redshift. This is how the formula of the redshift is. After this, to calculate the recession velocity, just multiply the redshift with the speed of light. That's 300,000 kilometers per second. And this is what we get the recession velocity of the specific object that we are studying. So this is how we calculate the redshift and the recession velocity of the specific object in this space. So this is what I studied. I'm studying in the spectrum from the SDSS Slow Digital Sky Survey 16 data set. This is a sample galaxy I took to study. So this was the observation line of oxygen. Here are the observation line of nitrogen and sulfur. And here are more observation line. I don't know what are these. I don't have learned this that these are the observation line of nitrogen and sulfur, but if you do research or you study the original data, you get to know, you get learned actually with time. So if you see here, this is zone 3, oxygen 3, and this is also oxygen 3, and I am studying currently about the oxygen 3 and making a Gaussian fit. So the Gaussian profile is actually the profile used to make plots, make to fit plots in the astronomy and every part of the data analysis or machine learning. So this is what all about. So thank you for joining our session. Thank you for joining our webinar. If anyone want to join our club, you can direct to this website and fill the form. You will be added soon. Thank you for your time. Thank you for so much precious time. And you can discuss anything you like now.